So I think this is where we got to. So we had looked at that pressure difference that allows oxygen, or well, the air, to move from the atmosphere into the lungs. And we looked at the pressure differential between the lungs and the bloodstream that helps the oxygen move across and into the bloodstream. So now we're going to take a bit of a look at, once it's in the bloodstream, how does it get transported around, and then how do we see oxygen being offloaded at the correct place to make ATP. Okay, so I'm going to keep this as simple as I can because there's a couple of items in the rest of the chapter that get a bit mind-blowing. Okay, so we get oxygen into the bloodstream. It doesn't dissolve, not very much of it dissolves into the plasma of the bloodstream. Most of it gets picked up by hemoglobin that sits inside the red blood cells. Okay, so about 98% is transported sitting on the heme part, so that heme lets us know that we need iron in there. Okay, and so it sits on the heme part of the hemoglobin molecule, and they use fancy terms for if we've got oxygen sitting on the hemoglobin, they call it oxyhemoglobin, and if there isn't oxygen there, deoxyhemoglobin. Not quite sure why we have to distinguish that, but and so how much hemoglobin is available is going to dictate how much oxygen can be moved around the body. Okay? Now, because iron is necessary for the hemoglobin to do its job properly, then we have a link between what we call anemia and low oxygen carrying capacity. So if someone has anemia, that can severely affect their ability to do aerobic work or endurance work. Okay? So anemia can be caused by a couple of mechanisms. It can either be that your bone marrow isn't making enough red blood cells, or it could be that the red blood cells, for some reason, don't have hemoglobin that is working correctly, i.e. there's not an iron there, or it could be some combination thereof. Okay? So the primary anemia that we see, the most common anemia that we see across the world, is this iron deficiency anemia. So that can be caused because I don't eat enough foodstuffs that have iron in them, or it could be that I'm eating the right foodstuffs with iron, but for some reason I'm not absorbing it properly. Okay? Those are the typical reasons. Then there's extreme situations like if I have an internal hemorrhage, then that could cause anemia, or pregnancy can cause anemia because the body will prioritize iron to the baby. Heavy menstruation, so if you go on and work with female endurance athletes at any point, then if they have particularly heavy menstrual cycles, they could be anemic for some point of the month. Okay? So what we want is this saturation. And what they've noticed in athletes, although there's a box in the chapter that talks about this, and they say it's not as common as people used to think it was, but when we talked about the cardiovascular system, we said that one of the adaptations to training is an increase in blood plasma volume. And so what can happen over those first 2 to 3 weeks of being back in training is that we get an increase in plasma volume without an increase in red blood cells. And so it can identify as anemia. They call it sport anemia. But once the blood plasma settles down and by training we start to create more red blood cells, it evens itself out again. So it's not a permanent situation, it's just a short-term scenario that can occur. Okay. All right, big long words again. Oxyhemoglobin dissociation curve. It's quite a mouthful. And we're not going to look at this in very much detail, enough to understand how it impacts oxygen delivery. All right, so what it represents for us and explains, if you're really good at graphs, but it's a bit over my head sometimes, is how do we dump oxygen onto the hemoglobin at the lungs. It travels around the body and it knows the right place for the oxygen to be dumped back off again, right? And so that's what this curve is trying to show in a way, okay? So here, this would be 100% saturation, all right? So blood in the systemic arteries, so this is the blood leaving the heart and being pumped around the periphery, okay? So when it leaves the heart, it's hopefully 100% saturated. Over here, we have blood in the veins coming back to the heart, and we have a lower level of oxygen that we talked about before in the veins because some of the oxygen has left and gone into the tissues, right? So between this point and this point, that part of the curve represents the amount of oxygen that was delivered to tissues and organs and what have you, okay? And one of the things, one of the applied pieces of information that the textbook gives us here that I think is quite interesting, particularly when we get further on and we start looking at altitude training. This flattening of the curve up here allows for the fact that we can have only 90%, 90 millimeters mercury rather than 100%, 100 millimeters mercury, and we still can offload a lot of oxygen, which is useful if you go up in altitude just a little way. So if you go from sea level to 2,000 or 3,000 feet, this little flattening of the curve is what allows performance not really to be affected, okay? So the book talks about 3 different effects that we see on this curve. I only want to cover 2 of them. The other one is more chemistry-based than we need to go, in my opinion, okay? So we're going to talk about the effect of temperature and the effect of pH, right? Acidity, alkalinity levels. So again, the main thing we want to understand is that the curve is trying to show us how and where the oxygen can get dumped off at the right bus stop. right? Because if I'm running and all the oxygen is being pumped into my chest muscles, then I'm not going to be able to run for very far, right? It has to be able to tell the right working muscles that need the oxygen. And how that happens is because of temperature and pH, okay? So when temperature goes up, the curve shifts to the right. And what that means, even if we can't read the curve, what it means for us is that it decreases the affinity of the hemoglobin for oxygen. Right? So that means if I've got an increase in temperature, it's easier for the oxygen to get off the hemoglobin bus. Okay? If I see a decrease in temperature, then the curve moves to the left, and that makes it harder for oxygen to get off the hemoglobin bus, right? It increases the affinity of the hemoglobin. It like turns up the magnet and holds on to the oxygen even more. And if it gets warm, it turns down the magnet and the oxygen can plop off and into the muscle tissue. Okay? So that's quite interesting because that means when it's cold outside, right, one of the reasons it's harder to get going, right, and we have to warm up more is because if our temperature is a little bit chilly, because we're outside in the cold, that oxygen can't move off into the muscle as easily. Okay. We see a similar effect with pH. All right? So if we see an increase in acidity, the curve moves to the right. Right? Makes it easier for oxygen to get off the bus. If we see a decrease in acidity, the curve moves to the left, makes it harder for oxygen to get off the bus. Okay? Now, the bit that we want to understand, in my view, right, is that these shifts to the right that allow oxygen to more easily leave the hemoglobin occur when it is warmer and when acidity is higher. And both of those things happen when we exercise. Right? So the working muscle, the muscle that needs the oxygen the most, is going to be the warmest and have the highest levels of acidity. And so oxygen can jump off into the correct muscle. Okay? Did that make any sense at all, Chris?
I gotta keep reminding me to turn my mic on, but yeah, it makes sense.
Yeah, it is.
Yeah.
I reread this bit of the chapter basically every semester, and I still find the depth of information that they go into in this chapter a little over my head, to be honest. That's why I like to simplify it a bit so that we understand that the heat and the increase in acidity is the thing that increases delivery of oxygen to the muscle. Okay?
Yeah.
All right. So before we look more closely at this, we also want to think about what's happening with carbon dioxide, right? Because if we're working aerobically, we are making carbon dioxide. and we have to transport that in the bloodstream back to the lungs to get breathed out, okay? So again, not very much of the carbon dioxide can dissolve in the plasma, only up to about 10%. About 20% can attach to the hemoglobin, but not the heme portion where the oxygen attaches, the globin portion. So there isn't like a conflict there. There's not a competition for space on the hemoglobin because they take up different portions of the molecule. Okay? The majority of carbon dioxide, about 70% or so, is transported as bicarbonate, which releases, when it's turned into bicarbonate, it releases hydrogen, so it increases the acidity. So all these pieces of the pie all work together to make it much more, much less of, let's go the other way, much less of a complicated process to get oxygen into the muscle. Okay? So, I'm going to redraw this because they have this diagram in the book and it's horribly messy and complicated. So I'm going to do a slightly simpler version for us.
Your joints tend to L2.
Sorry?
I said your joint tends to L2.
Yes. All right, here's my red blood cell. Okay, and let's have purple for the bloodstream. Woo! Sorry, that's a capillary. And let's have blue for the lungs. Oh, good. Horrible drawing. It's so hard to draw with a mouse. Okay, so here we've got the lungs. And over here, we've got bloodstream. Okay? So, what we want to look at is the movement of oxygen backwards and forwards, thinking about our high-low concept. Okay? So, in the lungs, right, oxygen is high, right? And remember that in the bloodstream coming from the heart to the lungs, oxygen is low. Okay? So, if we trust our physics law, right, that means that oxygen is going to move from the lungs to the bloodstream. All right? I don't need blood here. Let's correct that. I need muscle. Ignore the blood. This is the muscle, the purple. All right? So, oxygen was high in the lungs, low in the bloodstream, coming from the heart to the lungs. Therefore, oxygen can easily, remember the car on the hill, right? There's a steep gradient here, makes it relatively easy for oxygen to cross over into the bloodstream. Now, when we get to the muscle tissue, the oxygen pressure in the blood is the same as it was here, but the relationship is different, right? Because when it gets to the muscle tissue, the partial pressure of oxygen in the muscle tissue is low. Okay? So now that oxygen has a simple transition from the bloodstream into the muscle tissue. All right, so what's important to understand when you look at this is that the partial pressure here and the partial pressure here are the same. It's the relationship with the partial pressure on the other side of the membrane that makes it high or low, not the actual pressure itself. Does that make sense?
Yeah, I'm following.
Yeah? Okay.
Yeah.
All right. So now we'll look at carbon dioxide, right? So relatively, because we're making carbon dioxide within the muscle tissue, it's high inside the muscle, and it's low in the bloodstream, right? So that means that carbon dioxide can leave the muscle tissue and move into the bloodstream. Okay? When we get round to the lungs, we want to dump carbon dioxide out of the bloodstream into the lungs so we can breathe it out and the trees and the plants can all breathe it in. Right? So here, the same partial pressure, but in relationship to the pressure in the lungs, now we have more carbon dioxide in the bloodstream and less carbon dioxide in the lungs, because at sea level, carbon dioxide is only 0.2 millimeters of mercury or something. So when we breathe in, there's very little carbon dioxide in that air that we breathe in. So then this allows carbon dioxide to leave the bloodstream, get dumped into the lungs, and get expelled by breathing out. All right? So again, the partial pressure of the gas doesn't change from low to high. The relationship of the pressure is low here compared to high in the lungs, high here compared to low in the muscle tissue, and vice versa when we look at carbon dioxide. All right? So this diagram that I drew on the whiteboard is saying the same thing as the technical one in the textbook. They show a lot more detail because they show the carbon dioxide going to bicarbonate and then going back to carbon dioxide and then getting dumped into the bloodstream, because that hydrogen ion is important when we look at respiratory control. All right? But I think the one in the book is quite difficult to look at. This is much more simple, hopefully. All right?
Yeah, this one's like more to the point.
Yes. Yes. This tells us applied people what we need to know, I think. Okay, let's go back to our... Okay, so on that whiteboard diagram we said that oxygen can leave the bloodstream and move into the muscle tissue because the partial pressure in the bloodstream is higher than the partial pressure in the muscle tissue. And we see that on this diagram here. If you, this top part of the diagram we saw in the previous chapter. If you come down here, right, we've got partial pressure leaving the left ventricle of about 100 millimeters of mercury. And when we get to the muscle, the partial pressure is only about 40. So we've got a 60 millimeter difference. That's a very steep curve gradient, right? So that means that oxygen can very easily offload into the muscle tissue. Okay? So oxygen can get in, carbon dioxide can get out. Okay, so we've got oxygen into the muscle tissue. That's great, step one, right? But if we remember back to the beginning of the semester, and we dig around in our grey cells, somewhere in there we remember that we need oxygen in the mitochondria because that's where aerobic ATP is produced, right? So it's not in the mitochondria yet, it's only in the muscle cell, right? The mitochondria is floating around in the plasma in the cell. So now we have to get the oxygen from the membrane to the mitochondria. And we have a molecule that's very similar to hemoglobin called myoglobin. So myo, anything, is to do with the muscle. Okay? And it's a transport molecule that's similar to hemoglobin, and it's found in both skeletal and cardiac muscle, understandably, since we know that cardiac muscle only works aerobically. Okay? It binds with the oxygen and it assists in moving the oxygen from the membrane of the muscle cell to the mitochondria. Okay? Now, when we first start moving, there's already then some oxygen in the muscle cell sitting on these myoglobin molecules. Not very much, but enough to help out at the beginning. Right? So we said that very rarely do we only see 100% ATP-PC or 100% aerobic metabolism. Right? Usually all three energy systems are kind of chugging along, and it just depends which one is predominant. Okay? So the way that aerobic metabolism chugs along a little bit and helps out at the beginning of movement is because we've got this little bit of oxygen sitting in the cell already. Okay? When we talked about EPOC, remember that excess post-exercise oxygen consumption, and we said one of the reasons we see this larger oxygen consumption when we finish exercising is to replace the oxygen that we stole at the beginning. This is where we steal it from, right? So we have to put it back. Okay? Type 1 muscle fibers, because they're the ones that are really, really good at aerobic exercise have higher levels of myoglobin. Understandably, they've got higher levels of mitochondria. Okay? Type 2A have lower levels of myoglobin, and type 2X have the lowest levels of myoglobin, because type 2X are very bad at using oxygen, if at all, to make ATP. All right? So it's logical. Try to look at the big picture of how everything fits together, rather than memorize little pieces. Right? If I understand that type 1 does the most aerobic work, then it would necessarily have the most mitochondria, and therefore it would be beneficial for it to have the most myoglobin. Right? I don't have to learn all those pieces, because they all sort of fit together naturally. Does that make sense? A little bit, maybe. All right, so how do we control breathing? Because it can be voluntary, but most of the time it's involuntary. Right? Most of the time, particularly like right now, I'm not thinking, oh, I have to breathe in, and then I talk, and then I breathe out, and then I talk, and then I breathe, right? That's not going on. I'm just breathing somewhere in there, right? Same for you, probably. So how is that involuntary breathing controlled? Okay, so pulmonary ventilation, breathing. So in the pons and the medulla in the brain, we have what is called a respiratory center. And it's responsible, it kind of works like a pacemaker. And it sets the rhythm for breathing, and it sends signals down the spinal column to the respiratory muscles, the diaphragm and the intercostals, to contract and then stop contracting and then contract, right? So we have this kind of breathing rate that is controlled by this respiratory center, and we have a rhythmical breathing pattern that we're not thinking about, right? We're not consciously controlling. Then we have some other ways of impacting breathing rate and depth. So we have another brain center in the medulla, although it's not in the same place. Right? And that's got chemoreceptors in it that are very, very good at identifying the level of hydrogen ions in the bloodstream. Okay? We also have chemoreceptors in the carotid artery going up to the brain, and chemoreceptors in the aorta that is carrying blood from the left ventricle out to the body. We have some stretch receptors and chemoreceptors in muscle tissue and in the lungs. So all of these other receptors are sending information to the central nervous system all the time. All right? So at rest then, we have relatively high levels of oxygen, low levels of carbon dioxide, low levels of hydrogen ions in the bloodstream. And that leads to low breathing rate for pulmonary ventilation, right? The central nervous system is going, okay, there's plenty of oxygen to sit still, there's not a lot of carbon dioxide that needs to be breathed out, we don't have an acid problem right now, we don't need to be breathing very hard. Okay? When we exercise though, everything goes kaplooey, of course, right? So when we exercise, We have relatively low levels of oxygen in the bloodstream because it's all being dumped into the muscle tissue. Relatively high levels of carbon dioxide as the waste product to be got rid of, and relatively high levels of hydrogen ions, making the bloodstream more acidic. That stimulates the respiratory center and all these chemoreceptors to send signals and go, okay, you've got to breathe way harder now, right? Because we need more oxygen. There's too much carbon dioxide. We've got to get rid of this carbon dioxide and get more oxygen into the system. All right? Now we can take over. We are able to breathe voluntarily, so we can hold our breath, right? The terrible twos, the tantrums that 2-year-olds will have, and they'll just hold their breath. And mum and dad are panicking because they're holding their breath and they refuse to breathe. The problem is they will breathe, so just ignore them and let them get on with their tantrum, right? Because ultimately, the involuntary control of breathing is the master. And I may hold my breath for a while, or decide to breathe harder for a little while, and eventually that involuntary control will kick back in and go, okay, I've had enough of this. I'm taking charge, right? This is why people drown, okay? Because you're in the water, you hold your breath, you're sinking. If you can't get back up to the surface for whatever reason, eventually, your central nervous system will make you breathe. Because your carbon dioxide levels are rising higher and higher, and your hydrogen ion levels are rising higher and higher, and that turns on breathing. And you breathe, and you get a lungs full of water, and you drown. Okay? Swimmers will use this mechanism to kind of cheat. It's not cheating, but it's sort of to cheat on their dive into the pool. So if you watch sprint swimmers who are going to be on a block and dive in on a gun, right? You'll often see them breathing very, very fast and deeply. Right? So they hyperventilate, okay? They overbreathe, right? And they'll go, get ready, dive, right? So when you don't understand what's going on chemically and with the respiratory center, people think, oh, they're breathing in more oxygen, so that they can hold their breath under the water for longer. We're more aerodynamic under the water. So if I'm a sprint swimmer, I want to stay under the water for as long as possible before I have to break surface and start a stroke, right? They're not breathing in more oxygen. They're breathing off carbon dioxide. Because if they can blow off enough carbon dioxide, they can trick their brain into lowering the breathing rate. And they don't have to take a breath for much longer. So they can stay under the water. Pretty clever, right? It's an advanced technique. This is not something you want to teach to beginners. I've seen sprinters use it when I'm watching like the Olympics or World Championships or something. I've seen sprinters do it because then they can get further down the 100-meter track before they need to waste energy breathing, right? I don't know that I've seen it anywhere else, but it's a very, as I said, it's an advanced technique. It's not something to teach to a beginner. If you run your own gym, or if you are a personal trainer, or a coach, or even a PE teacher, one of the one of the tools you want in your medical kit is a brown paper bag, right? Because when someone hyperventilates, not in this swimming scenario, but like a person who's training hyperventilates, it's very, very scary, right? Your fingers start to tingle, and your face and your lips start to tingle, and then you can't breathe. Because if I'm hyperventilating, for whatever reason, right? I've done a really hard run on the treadmill, and I'm very puffed out, and I'm blowing off all this carbon dioxide, my brain turns down breathing. And I've done it once in my life, scared the shit out of me and my daddy. He took me to the ER because he thought I was dying, right? You literally can't breathe. Like, your chest just seizes up and you can't breathe, okay? So, brown paper bag over the face, get them to slowly start breathing, right? I breathe carbon dioxide out into the bag. That means I breathe more carbon dioxide in. That turns the breathing rate on. And the hyperventilation will sort itself out. The skewy chemistry in the bloodstream will sort itself out without having to go to the hospital. But you need the brown paper bag. Any questions on that?
No, I'm good.
Okay.
So, it's actually, that's what I've seen like in shows and stuff, that they are using the paper bag to breathe.
Mm-hmm.
Yeah, so, no, I'm getting to understand like why.
There you go, now you do. It's just a brown paper bag. It's easy, it's cheap. You just make sure you've got some sitting around in your medicine kit, and bingo, you can solve the whole problem. But it's very unnerving. So the person you're trying to get to breathe is likely to be panicking a little bit because they don't understand what's going on, right? Okay, so let's have a look at what happens with breathing when we exercise. We don't really see adaptation in pulmonary ventilation. So we'll talk about that in a second. So we've got this curve here, and it's a similar idea to what we see with heart rate. Okay, here's the start of exercise. But if you look at the curve, the breathing rate actually went up a little bit beforehand, right? The same thing happens with heart rate with experienced exercisers. When they're getting ready to go and exercise, heart rate has already started to rise to get their body ready to do the exercise, right? Phase one here, at the start, so we see this rise, right? It's quite an abrupt increase in ventilation because of anticipation, and then we've got stretch receptors get going in the lungs, and they stimulate breathing even further, and so then before we know it, we're in phase two while we're exercising, and depending on the kind of exercise that we're doing, if we are doing something that is aerobic, then we will reach phase three, which is steady state, right? So think about when you go for a run or you go for a bike ride, and the first few minutes, you seem to be breathing quite hard. And then before you know it, if you keep going, your breathing kind of settles into this pattern that is quite comfortable, right? Because when we're in steady state, we're at the point where our depth and rate of breath is bringing in enough oxygen to manage the workload that we're doing. So it can just chug along, unless we hit a hill, then it'll go up again, right? Or until we stop. And then when we stop, this bit here is our epoch that we talked about before, right? We don't stop breathing hard the minute we stop exercising. It takes a while for our breathing to get back to resting levels. Okay. So, adaptation. As I said, typically we don't see adaptation in the pulmonary system. For most people, not being able to breathe enough is not a factor in exercising. Unless I had asthma, or I'm a smoker, anything where the bronchioles would be constricted for some reason, then it's a little bit different, right? But for a typical healthy person, I don't stop walking because I suddenly go, oh my goodness, I don't feel like I can get enough air. Right? Hardly ever happens. So not only is the heart highly aerobic, the respiratory muscles, the intercostals and the diaphragm are highly aerobic. They're very, very good at using oxygen to make ATP. So they don't get fatigued very easily. I mean, you have got to go a long, long time for those muscles in around your ribs to feel tired, right? It does appear that they might be trainable to a small degree. So again, swimmers and sprinters might do some kind of exercise where they're training these muscles to be stronger. But we don't see any change in the lung tissue. We don't suddenly develop more capillaries around the lung tissue. We don't develop more alveoli, right? There's no change in the lung tissue, it just is what it is. Okay? And I think that's it. Look at that, just on time. Perfect. Questions, Chris? Oh, where'd he go? Are you there? Oh dear, he got disconnected. Yeah, I see you got disconnected. Are you back now? There we go, you're coming back in, hopefully.
Can you hear me now?
I can, there you are. Okay.
I was feeling like I was good with everything so far. I just gotta like go over it.
Go over it. Yeah. So Monday will be a review session. Okay. Wednesday will be exam day.
Hopefully I ain't the only one in the class that Monday to do a review.
Hopefully, because the last one we did, no one showed up. So we didn't actually do a review for the last exam because no one came. So yeah, come if you can, that would be great. And then Wednesday, the exam is set to open at 6 o'clock in the morning and close just before midnight, Wednesday night. Okay?
Yeah.
All righty. Well, have a lovely weekend. Stay safe. Because Corona's having a kick it back. And I don't want any of you guys to get sick. So stay safe, use your masks, all that kind of stuff. And I'll see you on Monday.
Thank you. Enjoy the weekends too.
Thank you. Bye.
Bye.